Hello everyone and welcome back to the TheRacketChannel. It's been a very long time ago since I made the last episode. There were so many things crossing my ways, good things and bad things, interesting things and disasters. But now I thought it's time to make a break. I can't wait anymore for better times to come where I have more resources spoken in terms of time or personal health state or whatever you could rely on when you're talking about resources. So I thought I'd just gonna make a new episode now, and it's gonna be a short episode because this is a topic that isn't too much complicated, but it's really worth to hover a while over it, because it's one essential thing that always comes up when you talk about programming languages like Lisp and Scheme and Haskell and all those functional languages. And this is recursion. Recursion seems to be something that is something like a miracle, that is a little curious or has some magic attitudes. And I think a small sequel over recursion would be good to clarify what recursion really means. Recursion in fact is a very powerful mechanism. It means nothing more that you have some kind of algorithm. You enter the algorithm with some kind of parameter, it's a variable, and then the parameter is processed and a result comes out at the end of the algorithm. So there's nothing special in this. This is a more or less linear process, but you could imagine that you would feedback the result again to the input of the algorithm. So this is something you know from electronics, for example. It's a feedback loop. When you're looping back some of the, let's say, contents of the output of an amplifier, for example, back to the input, and normally you get some kind of self-oscillation. There are similar effects when you're doing this in software with recursion. So for example, fractals are very interesting results of recursion. But there's another process, it's called looping, which is more or less the same but done in another way. And both of these processes, of these approaches, have their plus and their minus. And I want to show you what recursion is on a small example I prepared for you. And we're going to take a look at this now. Okay, so here's a very simple example of what recursion is all about. This is a simple function that adds all the elements in a list and makes or calculates the sum out of it. That means 0 plus 1 plus 2 plus 3 and so on and so on. And this is done by recursively calling the function addList. So we start by invoking addList, and we take this list we defined here, going from 0 to 9, as a parameter. So the body of the function is very simple. We have a condition statement here that distinguishes between an empty list and everything else. If the list is empty, just a value of 0 is returned. When the list is not empty, then we print out some text here just to indicate on which level in the call stack we are currently, and then we add the first element of the list. For example, when we start the list, this would be 0, and we add it to the return value that addList gives back by taking the rest of the list from 1 to 9 as a parameter. So you can already see here that all the thing here sums up to, let's say, to a sequence of addList calls. And all those calls are wind up in a, let's say, in a stack trace. And after the last value, in the last call, which is always 0, this one here when the list is empty, the last value here was returned, then all these additions are made, and in this case, in the last case, the result is calculated. So when we start this here, you can see we start here with the first element here. I don't know why this is a 1. Okay, let's skip this for the moment. We start with 1 and we add the result of the next add list call by taking the rest of the list going from 2 to 9. And in the next call level, we take the first element of this already reduced list, which is the number 2, and we add it to the result of the add list call, taking the rest of the list going from 3 to 9. And you can see that this nicely sums up to the point where the list is empty. And when the list is empty and the last value was returned, then all these additions are made and the result of 45 is returned. Now you can see that on one side this is a very powerful mechanism for easily doing tasks that have a repetitive character. So you can break down what you want to do in calls and subcalls that iteratively or recursively go down until you reach some kind of termination condition. This is very important. If you don't have a termination condition, then your system will wind up results forever and this will screw up your whole PC. This is usually the case when you have an exhaustion or let's say depletion of memory stack. So all the memory stack was consumed by your application. Sorry. But apart from this is a very powerful mechanism. The problem is, as I said, with the memory consumption on the stack, that every time you do a new call of add list, you have a little space required from the system for the function call. That means at least the return address has to be put on the stack, and maybe you have some local variables also have to be put on the stack, and you have this list here, which is the variable. This has to be put on the stack. So this is eating up a lot of memory space if your call sequence becomes very long. So this is something you have to obey when you're doing recursion. There's another way you can do the same function here by using a loop. There are loop structures in TheRacketChannel, it's very powerful. You can see we have something similar here. We have the same list and we apply the list to a named let loop. A named let loop is simple to for next statements or while statements, you know, from other programming languages. So we have two parameters here in the loop. One is the sum, that means the addition of the already calculated values from this list, and we have the list itself. And we also have a condition statement here, and again, like in this example here, we have a termination condition. When the list is empty, we give back the sum. And in any other case, we print here some information text to see where we currently are in the, well, not in the stack trace, but in the let's say the calculation algorithm, and we call back the loop. But this is not a call in the name of recursion or in the meaning of a recursion. This is a call in the meaning of a loop. So we always give back the already calculated sum. So we start with the first parameter here with a 0, and we add 0 to the first element from the list, that is the 1, and we apply the rest of the list as a second parameter here to call loop again. And the second run, we already have the let's say intermediate sum, which contains 1, and then we add the first value of the list, of the already reduced or shorted list, with is the number 2, and we add it again to the rest of this by calling the next loop run. So we have a continuously updated value here of sum, and we also apply the more and more shortened list as a parameter in this loop construct. So that means we are not doing the final calculation at the end when everything has run down in the list up to its end. We are doing the calculation simultaneously alongside with our looping. And this is running in constant space. So that means you don't need always additional memory as in a stack because you don't do function call. This is just a normal looping process. So this is as well very efficient, and it takes care of your memory. So we're gonna start this now, and you can see first sum is 0. The list goes from 1 to 9. Again, here the 0 is skipped somehow. Then the second run, we already have a sum of 9 because this is the first element of the list. Is 1. The rest of the list goes from 2 to 9, and in the next run we have a sum of 3 because this is 1 plus 2. So this is continuously updated intermediate addition of the list that always refers to the parts of the list that were already calculated, and the rest of the list that was not calculated is returned into the loop as a parameter. So I hope you get the difference. Yeah, to see what you can do with recursion, apart from this plus and minuses I told you, you can use it everywhere, as I said, where you need something, when you need a process that is constituted by sub-processes that are equal or at least similar to the main process. So by always calling your algorithm again and again and again with maybe some slight adjustments in a parameterization, you can yield very powerful results. I made this little example here, which is a very short function that goes down to my directory tree. It starts with the current directory here. This is a function from Dr. Racket that gives you back the current directory as a path name. And I use this as a parameter to for the function directory list. That is also a library function from Dr. Racket. And directory list takes this path name and it gives you back a list of all the contents of the directory. That means files as well as other directories. So the trick is now that this little function I wrote named directory crawler takes this list and goes through every element recursively and adds them or glues them together to a list. This is done here by this cons function here. As you know, cons is a function is coming from Lisp and it's used to tie together single elements into a list. So we took the first element of the list, which is the first name of the directory list or the file list, and we added to the result of the next recursive call of the function directory crawler, which take the rest of the list. So when you take a look at only this part here, that means that this algorithm is climbing through the directory structure and just listing all the files in one directory level. But the interesting thing is now when the algorithm is facing an entry in the list that is a directory itself. And this is done here by this conditional named directory exist. This is a conditional that returns true if the path name refers to another directory and not to a file name. So that means if directory exists from the first element of the list here is a directory, then we again do a cons, and we cons another call of directory crawler with the expanded list of this new directory to our normal directory crawler call, which iterates through the files in the directory level we are already in. So this is very important, because you need to tie those both information strings together. If you do not so, like I did it here, then after reaching the first end of a directory, that means the end of a list, when this here, the nil statement or the empty list is returned, the whole algorithm would end. But we want to get all those loose ends together from all directory levels, and this is why I use this const statement, consing together the, let's say, the looping on the current directory level, and also the results of the looping of the next directory level. Sorry. And if we start this, you can see here in the output window with the respective path names what this algorithm found. So here a lot of normal files, as you can see, and you also can see this here, starting from there here to there is one list. That means it's one directory level. The next list is the next directory level. You can see it also here in the path name. This was the path name of the current directory level, and here we have another directory that has entered named tutorial1, and here you can see all those files of tutorial1. And now the list is closed again, and here the next level is entered, and you can see this is TheRacketChannel 2. This is also another directory, and it goes on until we reached the bottom. And you can see this result is mirrored in what you have here. Those are all those files, and this is the directory the algorithm went through with the names you already saw, and when it entered new directory level, it took all those file names and displayed it. And even if we have more nested levels like this one here, it goes down to the bottom of every directory path until it reaches the end. And this very powerful mechanism that really takes your whole directory structure, and it doesn't matter how complicated or how much nested it is, are just those few lines here. And I think this is really, let's say, an evidence how powerful recursion can be. But you always have to take care, as I said, because every time we are doing another call here from this level or from this level, we are consuming memory stack. And that means we're consuming space from the system. So that means when you don't take care, and even if you don't take care that your algorithm always reaches a termination condition, then you will screw up your whole system. So I hope this very important feature was interesting for you as well. It was for me. It's worth to take a deeper look in the Dr. Racket documentation to dig more into the details of these concepts of recursion and looping. What I found in documentation is that the developers of Dr. Racket also did a very good job in concerning what iteration and recursion means, and you will find probably the term tail recursion. And tail recursion means that the Racket compiler is designed in a way that is able to find the structure of a recursive loop, and if possible it makes recursion loop out of it that is more or less an iterative loop. So tail recursion in fact means that the result you are generating inside this this consecutive call of recursive call of functions only depends on the next function call and not on the parameters before. So that means there is no additional amount of memory stack that has to be consumed by local variables and stuff like that. So just the next variable of the result of the next function call is needed to complete the calculation, and that means that this whole thing is running in constant space. Sorry. So that's all for now. I hope it was a little interesting for you, and I would like to see you again on the next episode of the Racket Channel. Bye for now.